Alright, so the next problem that we're going to want to look at is we're going to want to be able to calculate specific volume given the pressure and temperature using the Cardano's formula. So what's the Cardano's formula? So if you scroll down to the bottom of this document, you can see that for the cubic equation in the form x cubed plus ax squared plus bx plus c is equal to 0, you can take these steps and find the roots. So this is similar to like the quadratic formula that you may have learned for, just a squared or ax squared plus bx plus c equals 0. And this is just for a cubic equation. So it's a very similar thing, just for cubic equations. So remember from an earlier video that we found a cubic equation for the generic equation of state in terms of the compressibility factor. So here I have that typed out here so we can reference it. You'll remember we had a z cubed term, we had z squared times, all of this, a z term times all of this, and a constant term. So that's in the same form that we're looking for. This blue parenthesis, that's our A, the pink one is our B, and the orange one is our C. I also have the compressibility factor definition written out here for us, because then we can find the roots of this equation and then rearrange it to solve for B, which is what we're looking for. Okay, so first thing we're going to want to do is code in the Cardano's formula into our Python. So I'm going to use the same Python workbook that I was using earlier in an earlier video. Okay, so we want to define, let's call this Cardano. We're using the Cardano's formula, so we'll call this Cardano. And so we'll define that, and our inputs are going to be A, B, and C. So we'll input what our A, B, and C are, and then it will calculate the roots for us. Okay, so what are we going to need to do to calculate the roots? First thing we need to calculate is this Q and this R. Okay, so I think I'm going to try to split screen this so that so we can see both at the same time. Alright, so scroll back down to where we were. Alright, so let's put in Q and R. So Q is going to be equal to parentheses A squared minus 3 times B over 9. Alright, and then R, that's going to be equal to 2 times A to the third minus 9 times A times B plus 27 times C. And then all of that will be divided by 54. Alright, so we've got Q and R in there. Next thing we're going to want to do is, so if we read right here, the next thing says that if Q and R are real, which is always true when A, B, and C are real. So we know that our A, B, and C are real, because we know what our A, B, and C are. So that works out. And then, so it says if they are real and R squared is greater than Q cubed. So we're going to have to write that clause in there. So if R squared is greater than Q cubed. Alright, so then what will we do? So then the equation has 3 real roots according to this, and we can find them by computing theta and then computing the 3 roots using these formulas. So let's start with theta. So theta is going to be equal to the arc cosine, so we can use np dot arc cosine for that, of r divided by q to the 2/3 power. or 3/2 power, sorry. 3/2 power. Alright, and then we can find our roots. And you'll notice here that the roots are pretty similar. It's really just what's inside the cosine that changes. So we can use an array to do that. So we're going to go, our roots are going to be equal to -2 times q to the 1/2 times np dot cosine of, okay, and then here's where we're going to put our array in here. So the first one we're going to have theta divided by 3. Next one we're going to have theta plus 2 times np dot pi divided by 3. Oh, that's not where the divided by 3 goes. So we want the theta also divisible by 3, so divided by 3. Alright, and then, alright, so our third one will be very similar, so we'll have theta plus another parenthesis of theta plus 2 times np dot pi, and then all of that's divided by 3. Oops, I just wrote the same one twice. That's supposed to be minus np divided by 3. Alright, and then after the cosine, then will be minus a divided by 3. Alright, so now we have our roots. So, you know, if that's the case it goes down, we want to return the roots. But maybe we want to, you know, sort these roots because we want maybe the smallest one first, the largest one last, just so that they're always in the same order. So we can do that by sort roots, I believe, something like that. It's saying that's an error, so I'm guessing that's not the syntax for that. The NP. Alright, let's try that. Alright, so it seems to have taken that. So, alright, now we want to do our other case. So what if you know, r squared is less than or equal to q cubed. Alright, so then that's where we come and scroll down on this document. And alright, so if q and r are both real, which we discussed above that they were, then we can use this and we'll have one real root and then 2 imaginary ones. So we don't really care about the imaginary roots because, you know, imaginary volumes aren't going to get us anywhere. So we're just going to worry about the real root for now. So we need to start with defining what a is. So we're going to have a is equal to the negative, and then the SGN sign function, we're going to do np dot sign of r. So that's just going to take, you know, the sign of r and use that. Alright, times, and then we'll have np dot absolute, so that's going to take the absolute value of r, and then add that to r squared minus q cubed, and then let's have another set of parentheses around that one. Right, and then 2, and then inside all of that, we're going to have that to the 1/3 power. Right, so I'm going to need a multiplication sign there. And I'll take the absolute value times r, or of r, and then, we're going to need the square roots of these. So that, so that's where we get the square root from. Okay. Alright, so we have that. And then next we need to figure out what b is. So if a is equal to 0, then b is equal to 0. And then else we've got, so that's when a is not equal to 0, we've got that b is equal to q divided by a. Alright, so we've got a and we've got b. We'll back out of that. And then we can calculate our root. So our root is equal to a plus b minus small a over 3. And then we're going to want to return this root. So return root. Alright. So that should be, oh, I forgot colon there. Also forgot that one. Alright, so we should be good now. So this is our code that's going to find the roots using the Cardano's formula. Alright, so we've got our function that is going to calculate the Cardano's formula if we input an a, b, and c. Now we need to connect this to the SRK equation of state that we've been looking at. So our goal for this problem is to input the pressure and the temperature and output the V. So let's make a function that's going to do that. So we're going to find a function. So the one we had up here that calculated pressure we called cubic P. So let's just call this one cubic V for similarity. And as I said, we're going to want to input the pressure and the temperature. Alright, so first thing we're going to need is we're going to need our epsilon, A, B, E, and sigma, or A, B, epsilon, and sigma values. So we made a function that did that earlier. Remember? Up here we made a cubic ABES function. So we can call that. So we're going to have A, B, E, and S are equal to, what was it called again? Cubic ABES of temperature. So cubic ABES of the temperature. Alright, so now we have those in there. And so next, we're going to want to use the Cardano's formula to find the roots. So we're going to have that our roots, so our z's, are going to be equal to, and then Cardano of, alright, so now we're going to have to type in our A, B, and C's. So let's get this, maybe, there we go. It's because it's in full screen mode, that's why it doesn't want to do that. Alright, okay, that's close enough. So, over here, I'm just putting this over here for reference. So our A is going to be this blue parentheses right here, so let's type that in. So we've got negative beta. Oh, so we haven't defined beta yet, we're going to need to do that, so I'll put that up there to remind us. So negative beta plus E times beta plus sigma times beta minus 1. Alright, so that's our first one. So now we need to do our B. So for our B, we're going to look at this pink parentheses right here. We're going to put that in. So we're going to have negative E epsilon times beta squared, and then I'm going to have minus sigma times beta squared, and then plus epsilon times sigma times beta squared, and then we're gonna have minus epsilon times beta, and then we're gonna have minus sigma times beta, and then finally for this one we're gonna have plus q times beta. So again, we haven't defined q yet, so let's stick that up here to remind us to define that. Right. So then, alright, so for our third one, that's going to be our constant term. So that's an orange hue. So now we've got negative epsilon times sigma times beta cubed, and then that's minus epsilon times sigma times beta squared, and then we'll have minus q times beta squared. Alright, so there we've got our A, B, and C's input into there. So now let's define beta and q. So you'll remember that. Alright, so here's what beta and q are. So beta is equal to B times P divided by, so beta, or B times the pressure divided by gas constant times the temperature. So the gas constant defined all the way up here at the top, so we'll know what that is. And then pressure and temperature input, and then beta, or B, it gets from there. And then Q is going to be A divided by B times gas constant times temperature. Again, all of this which it should have. And then we're going to want it to output Z. So return Z. Let's enter that. Alright, so remember that our goal for this problem is going to be to input the pressure and the temperature, and then using the Cardano's formula, output the volume. Right now we have the compressibility factor being output, so we want to change that to the volume. But before it can output the volume, we need to define what the volume is. So, and we can use that, and we can do that using the formula for the compressibility factor and just rearranging it. So that means that the volume is going to be equal to Z times R times the temperature divided by the pressure. Alright, so now we should be good to go. We can shift enter on that. And then I'm just going to shift through both of these just to make sure it's all good. Okay, so now let's just run a test case for this. So cubic B. So let's say that our pressure is 1 times 10 to the 7th pascals and 600 Kelvin. See what happens. Oh, I have a capital Z there, and it should be lowercase. Alright, so that doesn't quite look right. So that means I have something wrong up here. Alright, so let's see here. So we've got Q is equal to A squared minus 3B over 9. Yep, R squared is A times, or 2 times A cubed minus 9 times A times B plus 27 times C over 54. Alright, and then if R squared is greater than Q, oh, okay, so there's my mistake. See, R squared should be less than Q. So let's do it like that. Alright, and so now you can see that its output are 3 roots for us. So that's just for that specific pressure, that specific volume, temperature, and its output are 3 volume roots.